We're going to get started up here. It's 1 p.m. Welcome back, everyone, to our Coffee Shop Astrophysics series. We just wanted to highlight one more event that our planetarium at UWM is having this month, so check out their website if you're interested in that. In case you're just having coffee and have no idea what's going on, we are a group of graduate students from UW-Milwaukee. We're specifically a part of the Center for Gravitation, Cosmology, and Astrophysics, and we give talks here about once a month during the school year about something related to astrophysics. All right, today your speakers are myself, and Joshua will be following me up. If you have any ideas that you would want us to talk about, please feel free to email us those or come talk to any of us at the end of the talk. We're always open to different topics. But today, our topic is going to be somewhat of a question, and we're going to be trying to answer the question of how empty is space. We'll see how well we do. All right, so when I told a lot of my friends and family that I was giving this talk, and I told them the topic, most of them answered, pretty quick answer, well, it's very empty, right? Pretty simple, all done. Hopefully at the end of the talk, we'll make you ask another question, and that being, or is it? All right, so before we talk about how empty space is, we need to get a good grasp on how big it is so that we know what we're trying to fill. But before we answer this question, we're going to answer another question, and that is, how old is space? How old is the universe? Well, we know from something called the cosmic microwave background that the universe is about 13.8 billion years old. So the cosmic microwave background, or the CMB, is basically radiation that happened not right after, but close to after the Big Bang. So after the Big Bang, there was a lot of hot particles, a lot of light hanging out in space. Over time, that stuff has cooled enough that we can actually detect it in the far infrared and radio telescopes. So the CMB is essential in studying the early universe because it's the farthest back that we can see, and therefore the farthest point from us that we can see in space. So the age of the CMB also gives us a distance to the CMB. In astronomy, we use something called light years, and this is just the distance that it would take light or something traveling at the speed of light to reach us in a year. So we would say that the CMB is 13.8 billion years old, and that would make it 13.8 billion light years away, or it would take 13.8 billion years for light to reach us from that spot. So it's pretty far. All right, now that we have that distance, I could use my telescope, look at the sky, look at the CMB, and convert and say, maybe I can model the universe as a sphere with this radius of 13.8 billion light years away, and then we can calculate a volume and see how big we're trying to fill. Well, that's not entirely correct, and the reason for that is because we know that the universe is expanding. So one of the ways that we know this is from studying something called redshift. So galaxies or any cosmological objects that are moving away from us in the sky or in space, their wavelengths become stretched out as they move away, and this gives them a redder spectrum, and that's why we call it redshift. Oppositely, if something is moving towards us, their wavelengths get compressed, and their spectrum becomes bluer, so we call this blue shift. So we've been able to study the redshift of a lot of cosmological objects that show us that the universe is expanding uniformly in all directions. So there isn't a center of the universe that it's expanding around, rather it's uniform everywhere. I'm pretty sure we have a YouTube talk just on the expansion of the universe, so check that out if that sounds interesting. We're also able to calculate the rate of expansion. So we know that the CMB that we thought was 13.8 billion light years away is now 46 billion light years away. So this gives us a different radius for our sphere of the universe. And then if we tried to fill that sphere, we would get this volume of about 10 to the 80 cubic meters. So this exponent notation is something that you're going to see in this talk a lot since we're dealing with such large numbers. What this means is it's the number 10 followed by whatever number it's raised to, that many zeros after it. Okay, so if I were to write out 80 zeros, that would take up a lot of slides and be super boring. So shorthand, we just raise it to that power. So it's hard to even get a grasp on how big this number really is. All right, so now we have our volume that we're trying to fill. This talk is about emptiness, so we need a way to define emptiness. And to do that, we use the term density. In astronomy, there are two main definitions of density, one being mass density. This is probably what you're more familiar with in your everyday life. It's just the mass of something over the volume that it occupies. So for example, if you looked at something like a kickball and a steel ball, that steel ball would be denser. Mass density is mostly used when you're looking at single objects like a star. But the way that we're going to focus more on density today is using number density, and this is the number of objects per set volume. So this is really helpful when you're studying a large volume and looking at the number of objects in that volume. For example, if you're looking at a star cluster and you want to see how many stars are in that volume, you would use the number density. Another way to think about number density in your everyday life is if you're looking at a classroom. If the classroom is pretty empty, like 1 or 2 students, you would have a low number density of maybe 1. But if you had a full classroom with a bunch of students, you would have that higher number density, something like 20 or 30. All right, so the more objects would give us that higher number density. Okay, now I'm going to switch gears and tell you about something with no density that will be brought up in this talk. And that is what's called a photon. So the easiest way to describe a photon might be by calling it a light particle. However, that's not entirely correct because it behaves like a particle and a wave at the same time. So we have a lot of experiments that I think that we've covered in talks before that prove that light actually has the characteristics of a particle and a wave at the same time. A photon has no mass and therefore no mass density, and it travels at that speed of light, 600 million miles an hour. A better way to think about a photon might be by picturing it like a bundle of energy, because it does carry energy. So for this reason, it does have something called energy density, which makes these particles still essential in studying because they interact with objects around it via gravity since they hold that energy. So just because they have no mass doesn't mean that we forget about them. All right, so let's go back to looking at the universe as a whole. Through observations, models, and calculations, we've been able to determine something called the critical density of the universe. This number, basically, if we had any density higher than this number, the universe would curl in on itself, but we know that's not happening. We actually have a flat geometry in space, so that gives us this number as the critical density. This 10 to the minus 26 is a point, and then 26 zeros and a 1. So this is an extremely small number. And if we use our definition for density that I showed earlier, we can calculate the total mass we should find in space using that volume that I showed, and we would get something like 10 to the 54 kilograms. So that's a lot of mass. All right, we have 3 different types of matter that you would find in space. Normal matter, which we call baryonic. This means it's made of baryons, protons, and neutrons. This is the stuff that we see every day. We're made of normal matter. Everything we see here is made of normal matter. This only makes up somewhere between 1 and 10% of everything in space. We also have some spooky stuff called dark matter that I'm sure everyone has heard of, which makes up about a quarter, and then dark energy, which makes up the most. I'm going to focus on the first one, just that normal matter, and see how often we would run into something like that in space. All right, so let's start as small as we can and talk about atoms. Atoms are the building blocks of nature. They're made up of protons, neutrons, and electrons with that nucleus that's positively charged, protons and neutrons, and then the electrons orbiting them. This model for the atom was introduced in 1909 using something called the Rutherford experiment. And I'll show you. So basically what Rutherford did was he shot positively charged particles out of a radioactive source through a sheet of gold foil, and then they had a detector on the other side. So the interesting finding of this experiment was that most of those positively charged particles went straight through the foil to the detector on the other side. And what this showed was that most of the atom is actually empty space surrounding a tiny nucleus. So how they found this was because the nucleus is positively charged. So if you shoot positively charged particles at it, they should repel, unless there's a lot of space in between. So they had this model that the atom is mostly empty space. Okay, to give you an idea of just how empty it is, because atoms are so small, so it's hard for us to picture what empty space is on that scale. If you took a single p as your nucleus, the distance to the closest electron would be a whole football field. Okay, so that's how much empty space is really there. All right, and then when you put different combinations of numbers of protons and electrons, you get the elements that I'm sure you guys have seen in some chemistry class in your life on the periodic table of elements. And these are the elements that we find in space. All right, so now we're going to talk about the baryonic matter in the universe on a larger scale. And remember, baryonic is matter composed of those protons and neutrons, those atoms that I just talked about. So some big objects that might come to mind that we would find would be moons, planets and their atmospheres, and of course stars. All right, so let's see how much space those moons take up. Well, in our solar system, we have more than 200 moons, and NASA guesses that there are about 10 billion planets in our Milky Way galaxy alone. Along with this, we have an estimate of about 2 trillion of those galaxies in our entire universe. Okay, so let's assume that every planet has its own moon. Then we would get a guess for a number of moons in our universe as 10 to the 22nd, so 10 followed by 22 zeros. A lot of moons. However, the number density of moons would only be 10 to the minus 58 moons per cubic meter. So what this number tells you is that if you spread out all the moons in a uniform space, in uniform directions in space, you would have to look in a volume of 10 billion cubic light years to find one moon. So that would be pretty sad. So when we look at moons' compositions, they're made of mostly metals. In astronomy, we call anything that's not hydrogen or helium a metal, probably because we're lazy. I don't know why, but moons are mostly just composed of these metals. Something that might surprise you is if we go back to that guess for the number of moons in our universe, and we made an estimate of every moon being the mass of our moon, that would only make up this extremely small percentage of that total mass that I showed earlier. So these are really huge to us, but in the grand scheme of the universe, they don't really contribute to anything. All right, so maybe planets make up all that space. So let's do the same kind of calculation. If we guess that there are about 10 billion planets in our own galaxy, and then we model every of those 2 trillion galaxies as our own, we would have that estimate of 10 to the 22nd planets in our universe. So similar to those moons, you would have to look in a volume of 10 to the 58 cubic meters to find one single planet. All right, and then if we also did an estimate of every planet being the mass of Jupiter, which is the most massive planet in our solar system, we would again only get 0.001% of that total mass. So hopefully this is giving you an idea of how small everything is when you look outside of it. All right, so maybe the planet's atmospheres take up all that space. So if we look in our solar system, every planet except for Mercury has a pretty significant atmosphere. And then I just wanted to give you examples of the density of a couple of those atmospheres of different planets. And then for reference, the density of water is 1,000 kilograms per cubic meter. So you can see just from these 3 planets that Venus has the densest atmosphere, and it actually has the densest atmosphere in our solar system. All right, so Venus has the most massive atmosphere. It's made up mostly of carbon dioxide, a little bit of molecular nitrogen. It has this total mass, 10 to the 20 kilograms. That's huge. Well, when we again look at the grand scheme of the total mass, it still is this extremely small number, even if we slapped Venus atmosphere on every one of those planets. All right. Okay, so you're probably thinking, well, then it must all come from stars. Stars are way bigger than anything we've talked about so far. When we look in the sky at night, especially outside the city, we see billions of stars, millions of stars. They look super close together. They might even look like they're on top of each other. Well, we have an estimate of 10 to the 23 stars in our universe. But again, when we convert this to number density, you would only find 1 star if you're looking in a volume of 10 to the 57 cubic meters. And that's if we spread the stars out everywhere. All right, so they're not as close as they appear in the sky. This might lead you to ask a question like it did for me. Maybe, probably not. How far could you see in any direction before your line of sight struck a star? I thought this was an interesting question to ask. So to answer that, what we would do is imagine you're taking a cylinder of light from your eye. So we're modeling light as a cylinder and seeing how far it would have to go until it hit a star. So the distance before striking a star would be the length of that cylinder over the number of collisions it would have from hitting that star. All right, so some magic and some math. We would eventually get to this fraction of 1 divided by the star number density times star radius squared. And then if we use this number, 10 to the 9 stars per megaparsec cubed as that star number density. Megaparsec is a new unit for this talk. It's just a larger unit of distance so that we don't have to deal with those large exponents all the time. We would end up with a total distance before your line of sight would strike a star, 10 to the 36 miles. Okay, so you could think of this as you would have to walk from here 10 to the 36 miles in space just to hit 1 star. Probably not worth it. Stars are the most massive objects we've talked about so far. Our own star, our sun, has a mass of 10 to the 30 kilograms. It's made up mostly of hydrogen and helium, a little bit of metals in there. Again, if we assign the sun's mass to every star in our universe, that would still only give us 10 to the 53 kilograms. And if you remember from one of my first slides, we're looking for that total mass of 10 to the 54. So we're still missing some mass, which Joshua will touch on in a little bit. All right, and lastly for me, I wanted to show this animation to give you a bit of a better idea of how far out we're actually looking when we talk about this stuff. So if we're starting at Earth, and then, I'm going to speed it up so we're not here forever. All right. So eventually we'll go out to our own solar system, still within our galaxy. Takes a while because it's pretty big. So we're still within our own Milky Way galaxy. Might see some star clusters. And then eventually we'll get outside of our galaxy and you could see the classic Milky Way representation. And we're still going. We might be joined by some other galaxies. And then eventually a lot of those galaxies will come together to form what's called a cluster. And then all those clusters will come together, maybe form a supercluster. And we're almost there. And then we'll have clusters of galaxies together. So hopefully that gives you a bigger picture of how far out we're actually looking and how much space there is in between. But I'll turn it over to Joshua. Yep.
Testing. Hello? Hello? Okay, yeah. So I will be talking about, I will be continuing on with the emptiness, and we'll be seeing this as a perspective of moving away from Earth, like this video right here. So we'll be traveling through the void, where our solar system is, out to where other stars reside, and then even to where other galaxies, between other galaxies. So we'll start with the familiar, interplanetary space. This is what we're most familiar with other than Earth, our solar system. And this is all because of the influence of the sun. The sun is an extremely powerful object with a huge magnetic field. And this magnetic field actually extends up to like 90 to 100 times the distance from the Earth to the sun outwards. So this is where interstellar winds become too strong for the sun's magnetic field, and it's called the heliopause. So that's where the interplanetary space ends. And there's also a lot of debris out here from the early solar system. So within interplanetary space, if you were to expect a number density, you'd only find about 5 particles per every centimeter cubed. So this is a pretty, it's pretty close to a vacuum. And beyond interplanetary space is where we've sent Voyager 1 and 2. But let's talk about something that's not regular matter, but has a huge impact on the solar system, and that is neutrinos. So if you haven't heard of what neutrinos are, they are elementary particles. They can be best thought of as the cousins of the electron. So you've got the electron here with its siblings, and then you've got the neutrinos. So they're very light particles that barely interact with matter at all, and the sun produces billions and billions of trillions of them, up to 10 to the 38 per every second. So these are produced in fusion reactions, and we're being bathed with them all the time. So hundreds of trillions of them flow through you this very second, but they don't interact with you at all. So the sun's energy output is actually 1% neutrinos, and neutrinos make up about 0.3 to 0.5% of all the matter energy in the universe. So yeah, there's trillions flowing through you right now, but when they do interact through a medium, they can actually travel so fast that they're faster than light within that medium. So if you have water, light travels slower in water than it does in a vacuum, but neutrinos don't. They travel at the same speed. So we can actually detect this like a sonic boom. We have the equivalent of photonic boom. So when these particles travel through, they emit some radiation that we're able to detect with these large photomultiplier tubes. So they tell us where the neutrinos came from. And this is what a photonic boom looks like. So if you've got a particle traveling faster than light in some medium, it has a photonic boom. So now we're getting slightly farther out. We're out of our solar system. We're into interstellar space. And obviously I had to throw in the interstellar black hole. But the closest star to us is Proxima Centauri, which is 4.2 light years away. And on average, stars in the Milky Way are 5 light years apart. So this is a pretty empty space, and you'd be lucky to find 1 particle per every centimeter cube out here. Of course, you do have regions where you have nebulae, you have lots of gas-dense regions where stars are born. So you could get up to 10 to a million particles per centimeter cube in some places. It's mostly hydrogen and helium out here, just the first elements to be made. Very few metals out here, like Ali mentioned. And it can be cold or hot. This is actually a map of all the hydrogen within our galactic plane. So you can see this is where the galaxy's plane is, and there's a lot of patches of hydrogen just lying out here. So as we go through the galaxy, the density decreases from the center where the black hole is. This is the black hole at the center of our Milky Way, Sagittarius A star. And as you go outwards, the density decreases, number of stars decrease. And we're actually right over here at about 8 kiloparsecs from the center, or about 30,000 light years from the central black hole. And there's a lot of interesting stuff out in the interstellar medium. You've got molecular gas clouds, which are like star nurseries. Stars are born here. You've got stellar corpses and nebulae where they've died and left behind a lot of material. But as we zoom out further and further, we get to intergalactic space. And this is the farthest out we've been yet. And you'd be lucky to find 1 to 10 particles per meter cubed here. So within a 30 cubic foot space, you'd be lucky to find 1 hydrogen atom out here. So our galaxy is about 100,000 light years in diameter. So if you head out 50,000 light years from the center, you're out here where there's barely anything at all. This is what we call the cosmic web. So you've got clusters of galaxies and then long strands of gas that connect them together. So yeah, it's just like a giant web network. We call this the cosmic web. And something interesting to note is that when we first looked up, we didn't see everything we expected to. As Ali mentioned, of all the matter energy in the universe, 5% is the regular stuff we're used to, like protons and neutrons. Then 25% is the other 95% is this mysterious dark matter, dark energy stuff. But when we looked for this 5%, we couldn't find it. We were only able to account for about 30% of this 5%, which was strange because when we looked up in the sky and we measured the amount of hydrogen, and when we looked at the cosmic microwave background radiation, there were small irregularities that told us how much we should expect to see. And we couldn't find it. So people started wondering, where is like half this missing matter that we expect to see? And it was proposed that it's probably out between these galaxies and it's very hard to see because if this gas is completely ionized, it's not sending us any light, so it's practically invisible to us. And now we've seen that within this warm, hot intergalactic medium, about 50% of mass is here. So this is from the warm, hot intergalactic medium, and so is this. So that accounts for what we were missing, really. This should be warm or hot, so 180,000 degrees Fahrenheit to 18 million. I'd go slightly more than saying warm or hot, but that's what they say. And we look at this using oxygen absorption lines. So what does that mean? What is an absorption line, really? Well, let's go over it. So every element, you can think of electrons orbiting the nucleus, and these electrons have very specific energy levels. So if you get a photon to come here and excite this electron, it goes up. And if the electron goes down, it releases a photon. And this photon's wavelength is very particular. This is because of quantum mechanics. These are very specific values, and each element has its own signature. So hydrogen actually looks like this. These are all the lines that you will see in hydrogen, and only this is the visible area. So there's a lot in infrared and ultraviolet. But if you heated up hydrogen and looked at the light, it would look like this. You would see these very specific lines show up for hydrogen, and this is what would tell you that this is hydrogen that we're seeing. Or if you shine light on hydrogen and then look at the light, you would see the same lines missing because hydrogen is now taking these photons away. So this is what emission and absorption lines look like. They tell us what specific elements are, and so it's really helpful. So how do we see all this? Well, I mentioned we're using emission and absorption lines, and it's somewhere out here. How exactly do we see it? Well, you need something really bright to light up all these gases. Something bright like a black hole that's accreting a lot of matter and is giving off a lot of energy. A black hole like H1821, and Chandra X-ray Observatory was actually able to do this. So you have your very bright source here, and as the light travels through these long filaments, you see absorption here, 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 here. So we're seeing the intergalactic medium using bright sources that are backlighting these things. And since the emission line is the same, what really changes is the fact that at each point the redshift is different. Now, Ali mentioned that redshift is when things move away, the light waves expand. So at each point, we see the same line at different points. So it's really helpful to tell us how far away something is, what it is exactly, and how much of it is there. So this is how we were able to find the missing mass. Up until 2017, we really didn't know where it was. So let's talk about something even emptier now, because there are such places in the universe as voids. Voids and supervoids are regions of extremely low density in the universe with about 1/10 of what I already told you. So zero point 0.1 particles per meter cubed. And one of the most famous ones is the Boötes supervoid. So this region right here. There's quite a few of them around us. So we're here in the Virgo supercluster, and there are these voids that surround us. You can think of them as bubbles, and so when they come together, they can actually merge and grow together. And one thing that I wanted to point out is when you Google void, this image right here shows up, and it's actually not a void, because voids do not look like black splotches. You can actually see the stars behind. And you'll notice that the redshift of these stars is much higher than the stars around them, which is why we know that there's a gap in space there. And this is actually 330 million light years across, which means each end of this is moving away from the other at 4,000 miles per second because of the expansion of the universe. So this is a large distance. So yeah, these things are present everywhere, and there might be one or two galaxies present in here, surrounded by nothing else. Okay, so now I'm sure a lot of you have been sitting here wondering, talk about dark matter, talk about dark energy. Ironically, dark matter is such a dense topic that it could be its own, and has been its own talk, but I will go over the basics. So dark matter, as some of you may have heard, is this mysterious substance that doesn't interact with anything as far as we know. It doesn't give off, absorb light. The only way we know it's there is because of gravity. So when we looked at galaxies, and as I said, the density decreases, we expected the rotation of these galaxies to look something like this. As there's less mass out here, it'll get slower and slower. Except that's not what we saw. We saw that it actually almost stabilizes, which means that there's a giant amount of matter that we can't see that's surrounding our entire galaxy. And it's not fully understood yet. There's some models out there for what this could be. One of the most famous examples is the bullet cluster. So here the red are these gases that are in X-ray, and the blue is where we expect the mass to be. So you can see these two blue blobs moved right through each other, whereas the gas actually collided, interacted. So whatever this is, it didn't interact with itself, it simply moved through. So we know it's out there, we just really haven't seen it yet. And there are experiments similar to the neutrino thing I mentioned. There are these experiments with giant xenon tanks filled with liquid xenon and a little bit of gaseous xenon as well. And then moving on to a phase with 8 tons. So this is exciting information, but it's still in progress. And now dark energy. Okay, so I will come out straight and just say we have no idea. We really don't know what this is. We just know that its effect is expanding the universe. We know that when we've looked at supernovae farther and farther out, we've noticed them moving farther and farther away. So something is causing the universe to move apart from itself. And so this is anti-gravity. This is like repulsion. We think it's a property of space itself. And we're actually at a point in the universe's history where at one point there was more light density. Light was the most, occupied the most density, and then it went down to matter. And now we're at a point where dark energy is the dominant mass energy of the universe. So we're going to talk a little bit about dark energy, but in a different aspect, because I mentioned that this is a property of space, and it gets even weirder. So let's finally ask ourselves, what is emptiness? What is a pure vacuum? It turns out the answer is not what you might think. We've looked, and empty space isn't exactly empty. There is a 0 point energy or a lowest state of a quantum system that still has a non-zero value. So we see these fluctuations on the smallest scales of the universe where waves, full of waves and particles that come into existence as anti-pairs, annihilate each other, and this process repeats and happens on extremely small time scales. So I'm going to dash your hopes. We can't tap into this as an infinite source of energy because it's probably the same everywhere, so we can't draw anything out of this, so don't expect that. But there's an even bigger problem with this so-called vacuum energy. So vacuum energy, it sounds similar to dark energy. So when cosmologists looked, they said, okay, how much of this should be out there? Well, dark energy has an effect, but only over large distances. So when they did the math, they got 10 to the minus 9 joules per meter cubed. Now a joule is a small amount, and a billionth of a joule is extremely tiny. Well, quantum physicists said, okay, we'll do the same thing, except our method, we'll just sum over all the possible different waves that can exist. And their number was 10 to the 113 joules per meter cubed. So that's a bit off. In fact, it's so off that this is often called the worst discrepancy in all of science, because this is 122 orders of magnitude that's off. Just to show you how bad this is what it looks like. This is 10 to the minus 9 versus 10 to the 113. It's not looking good, really. And there's no real answer we have. They have been able to get the number down a little, but still a huge problem. So what effect does this quantum vacuum have? Well, surprisingly, it can have an effect on some of the largest things in the universe, black holes. Some of you may have heard of Hawking radiation, but it's essentially how a black hole dies. So if you think about these particles that can come into existence and destroy each other and then repeat this process, if this happens close enough to a black hole, one particle can get eaten and the other can escape. And the particle that escapes has now stolen energy from the black hole, and this happens over millennia until the black hole gets smaller and smaller, losing its mass. And as the black hole's mass decreases, this process gets faster. So for a black hole the size of our sun, this is going to take a while. It's going to take 10 to the 64 years. So don't expect to see any scientific evidence for this happening. We're probably never going to see it. But this is just an interesting aspect of how the smallest scales of the universe affect the biggest. So where does this all add up? Let's talk about the future of the universe and the emptiness within it. Okay, so our current models say the universe is expanding and it's accelerating. So if this is the case, everything will eventually spread apart from everything else. Everything will get too far apart to interact. And once all stars die, there's only going to be black holes left. And if proton decay is real, if a proton can actually just vanish into radiation, which we don't know about yet, then everything will eventually turn into just radiation. All matter will soon evaporate into radiation, and as the universe continues to expand, this radiation will get redder and redder until it's redshifted into oblivion. So once all black holes die, that's all there will be. And I know that's kind of a downer ending, so I'll leave you with some hope. The vacuum energy still remains. We know that dark energy's density is constant as far as we know. So, if there's quantum fluctuations and you want to be hopeful, this could maybe trigger a new Big Bang. That's just on a lighter note, But yeah, that is our talk. Thank you so much. So that's a good question. Parallel universes have been used as kind of there is a theory that says it's not for the missing matter, but more for this vacuum catastrophe that we see. People say that the reason why we're seeing such a difference in energy density could be explained by if you bring in like parallel worlds, but I'm not an expert on that, so I couldn't answer that. Yeah.
What is the measurement of a joule? Like, I don't, like, I've never really heard that term of measurement before, so what is that actually?
Okay. Yeah. So a joule. That's a good question. A joule is the amount. I think the easiest way to put it is it's the amount to raise 1 gram of water by only like a quarter of a degree Celsius. So it's a very tiny amount. Yeah.
Okay.
Is there like a more?
It's a unit of energy.
Yeah.
You guys could like definitively confirm or deny like one thing that you guys have talked about, like what would that be? Like what would be the most important thing?
So I guess I don't know. Do you have an answer for this?
Like with all the theories that we talked about, kind of. Definitively nothing. The thing we know the most about is that normal matter. So,
But like if you could, like what would be the most revelatory or like interesting thing that would have like the biggest implication?
I guess I would say, yeah, the quantum vacuum, just because we have seen its effects, but we still don't completely understand it yet. So, and it has a lot of implications on, the future of the universe and Einstein's equations of general relativity. So, I guess that's the most important or the most interesting aspect for me, I guess. Yeah.
So you talked about the universe being flat. Do we know where the center is, and are we in it?
so there is no center. Basically, you can think about it where wherever point you're at, everything is moving away from you at the same speed. So that means that there is no like center that's static and everything's moving away. But wherever you are, everything would be moving away from you no matter what point you're at in the universe. So when we talked about like the volume and everything, that's the observable universe. Universe is infinite, but that's how far we can see right now, and everything moves away in every direction.
Every point you're at is the center of the universe
Yeah.
for you, like.
Since this is a talk about space and distance, quantum entanglement, what's the farthest it's speculated two atoms can interact with each other?
Through entanglement? Well, there's no limit on that as far as I know. If two particles are entangled, you could send them to opposite ends of the universe and they'd still be entangled together.
I totally don't understand. I understand, but I don't understand. What are they, how can they manipulate each other?
If you can answer that, you would win a Nobel Prize probably. Yeah, we don't know.
Yeah.
That's about joule, so that's information. It's about a quarter of a calorie, so
Yeah.
a 40th of a stick of celery.
Okay.
Well, thank you everyone for coming. We'll, stick around up here if you want to come talk to us.
Bye.